Chevy inequality, you need to for decide on your K. So if this guy equal to this guy, then I will be able to find K to be equal to that. Okay. I'm using the idea of a standard deviation here because I'm assuming I'm working with an unbiased estimator. Okay, so when I plug the K in, okay, of course, when I square variance, when I square standard deviation, that's going to give me variance, right? Okay, so by the time you actually simplify this guy, you're going to have this. And of course, as n tends to infinity, when the variance tends to 0, we expect the probability of convergence of the point estimator to convert to the true value. That probability is approximately 1. Okay, so that's the information I'm trying to pass across. The idea of a Chebyshev inequality can actually be used to let me just tell you this. The consequence, one of the consequences of consistency of an estimator is that it will converge to true value of a parameter. Does that make sense? And that is how to show that is going to happen. Now, do you know variance? A sample variance is also an estimator. We may want to show a sample variance is consistent. You know, if I'm able to show that the variance of the sample variance, look at that, variance of sample variance, because sample variance also varies. Imagine 1,000 researchers go into a population to compute sample variance. They're working on the same thing, the same sample size. They're actually going to have different value for the sample variance. And because of that, we may want to see how consistent is the sample variance. The idea of consistency is going to come into play when something gives different results. At different location, I got different results. Okay, that's why we need to be able to investigate the consistency. Okay, so, and you know, before now, we've already established, we've already showed that the sample variance is an unbiased estimator of a population variance, and that is going to give us an idea that if I want to investigate the consistency of a sample variance, I need the variance and not the mean square error. Does that make sense? Now I'm going to repeat that. If I want to investigate the consistency of a sample variance, I need to be able to investigate is sample variance biased or unbiased. And I show you in this class that I show you this expected value of a sample variance actually give the population variance. Okay, I actually show you all of that. Okay, now, and this is going to tell me, oh, since this happened, I should be looking for this guy and not this guy. And not this guy. Does that make sense? Now, if I now want to, there are some, you know, we need to put some stuff into consideration or doing that. Of course, you know, the sample variance that we are actually talking about. Okay, so the sample variance that we are talking about, okay, the sample variance we're talking about is this. Right? This is a sample variance, right? Now, let's force. This is just a denominator. That's a constant, right? Let's work on this guy. That is what I'm doing here. I'm going to start working on that guy. Working on this guy now. Okay, working on that guy now. Take a look at this. We are all using the idea of mathematics now, algebra. Okay, now if I have y minus y bar all squared, okay, and I want to use this approach, that is going to be this, right? Algebra, we do the same now. Okay, when you do that, yeah, you multiply both sides by summation. Don't forget the summation is outside integral. Okay, the summation is outside integral here. Now when you take a look at this, then we move right here. That's after multiplying by summation. Each of them is going to have a summation sign. Situation where there's no random variable, the random variable here, y squared, the summation, we attract y and y squared, but where you have a y bar, anything y bar, their summation is going to turn to n. That's why you get this guy. Okay, now if you take a look at summation y, okay, if you take a look at summation y, if you take a look at summation y, of course, you know y bar is summation y over n, right? Then I can do summation y equal n y bar. So wherever I say summation y, I'm plugging n y bar, okay? When you take a look at the middle, I've already, n y bar replace summation y. Then I want to do algebra simplify that. That will be minus n y bar squared plus n y bar squared. That will finally give you n y bar squared. Any question about how we arrive here? Any question on that? So what are we trying to tell the world? We're trying to tell the world. We're telling the world that, okay, this guy is the same thing as that guy. That's our intention. That guy is the same thing as that guy. Okay? I told you from day one, if you really want to understand theory of statistics, the knowledge of mathematics is required. Okay? You can see what we're doing here. Now, we're not going to go back to the sample variance. Okay? Now, if you take a look at this, the last one, we've said that this guy is the same as this summation yi squared minus n y bar squared I start from 1 to n, right? And you know what? I can rewrite this guy as this. Right? Because y bar is summation y over n. Okay. Now, if you take a look at, if I want to bring out n, do you know, I can factorize and do mathematics as if n is common here and n is common here, bringing this n out, then I'm actually going to have this guy is going to be over n because this times this is going to be this, then I'm actually going to have this all squared. Okay, now, and that is what you see here. And this guy, you have an n here. Now, this guy is the same. Okay, now if I go back to my sample variance, that is this, divided by n minus 1, then it means I'm actually going to have, putting this guy now, don't forget this is going to be n over this guy. Then I'm going to have 1 over n here summation yi squared summation y over n all squared, which is what I have now. You see that? Look at that. Look at what so that is why you take a look at this now. Okay. Now we have this. This is like another way to write sample variance. Okay. We're playing around mathematics. Okay. Now, the next thing we want to do now, we want to look at the variance of y. Okay. From when I say variance of y, I'm talking about population variance right now. Of course, I'm going to do variance of y equals expected value of y squared. The variance of y here is different from this one. This is just sample variance. But the guy here is the variance of y. Okay. Now, if the variance of y equal to that guy, the first one here is what we call that, if you take a look at this guy, okay, that is second moment, and this guy, like the square of the first moment, and it is determinate. Determinate means the result you're going to have is less than infinity. Now, we want to talk about variance of y squared. Why variance of y squared? Oh, variance of y squared. Don't forget the other time I said I need the variance of this guy. I actually need, don't forget, I said I need the variance of sample variance. I need the variance of sample variance, not the variance of a random variable y, but the variance of a sample variance. Then I need to consider the variance of y squared first. The variance of y squared, do you know that using the same, if you take a look at this guy and this guy, what has happened? I squared them. The first one, instead of y squared, instead of y squared, y4. You square them. You see that? Any question about that? Okay, now I can rewrite this as fourth moment minus the square of the second moment. That is the variance of y squared. What you are telling the world, even in addition to y varies, y squared also varies. Okay, now we now want to, what you have here, the variance of y squared, has to do, we're talking about population movement, not sample movement. But can we have a way to use the idea of that, use maybe from the population movement, can we use the idea of a sample? But don't forget the central limit theory will enable us to do so. Okay, now I needed to take a look at this guy. Now I want to go by central limit, by law of large number first. Why do I need the law of large number first? Is because I want to talk about convergence. Law of large number talk about convergence. When sample size is large, something converges, right? Okay, but the central limit theorem is going to talk about the convergence of probability distribution. Now, I want to talk about if I want to figure out expected value of y, but by law of large number is trying to say sample mean can represent population mean. Do you see that? The sample mean is 1 over S summation y high. The sample mean is going to be a good representative of a population mean, okay? When sample size is large, there's going to be a convergence, and you can see a P there. That's a convergence in probability, right? The convergence in probability, the idea is being used. Now, if we use that for y, we're going to use that for y squared too. Look at that, okay? We want to believe that 1 over n summation y squared should also converge to the expected value of y squared, because the expected value of y squared is the population value. This guy here is the sample value. Don't forget, we always actually investigate the convergence of a sample to the population value. Any question? So far, so good, right? Okay, now, the moment I have this, I can impose some theorem, okay? And please, I need you to pay attention to what we're doing right now, okay? Now, I need you to take a look at this. If the g of s equal to s squared, okay, we can as well say that if I have 1 over n summation y converges to expected value of y, and 1 over n summation y square converges to that, then I can say the square. Now, do you know when this is going to happen? Because y bar converges to mu, then the square of y bar should converges to the square of the mean. That's what we mean here. Does that make sense? Okay, if that makes sense, then we can actually move forward. Okay, oh my God, look at what we want to do here. Okay, when you take a look at this guy, before a system converges, the element in the system, every element in the system has their true value. When the element in the system converges to their true value, then the entire system converges to their true value. Does that make sense? So if 1 over n summation y squared converges to this guy, and this guy converges to this guy, whatever algebraic computation, the algebraic computation here is minus, could be that or plus, it could be whatever, also going to converge to that. And if that happens, don't forget, this guy is the variance of y. We can as well say the variance of y is this guy. Because the sample converges to that. Take a look at that. And don't forget, I said the variance of y equal to that. Now, if that happened, let's go back to the variance. Oh my God, we're gonna take back to the variance now. I needed to pay attention to this guy now. This is the sample variance that we derived the other time. Okay, now let us now see whether the whole thing is going to convert to sigma squared. Take a look at what is going to happen now. Okay, now do you know that if you take since this guy, if you take a look at this, 1 over n summation y squared, as we said, okay, if you compare this with this, you're actually going to see at the end of the day, it's going to be that. You know why? Because when sample size is large, there's no difference between these. This is going to be 1. N over n minus 1 is going to give you 1 when sample size is large. It's just like I said, or something billion or trillion divided by, so it's big number divided by another big number. This is going to be 1. So this guy, n over n minus 1 is 1. And what about this guy? This guy is what we talk about here that converges to sigma squared. Any question? Look at that. Any question? Any question on what I'm showing you right now? Any question? Okay, now I'm going to move. Now, you remember the other time in chapter 8, we constructed bicentral limit theorem. We actually had a large sample interval, a confidence interval, okay? Assuming that your sample statistic, your estimator, approximately normal, with the mean of that and the variance of that. And if that actually happened, then we also expect us to say that this guy here is also going to be follow a normal distribution with mean 0 and 1. If this guy converges to theta, then this minus z divided by the standard deviation also converges to standard normal. Okay, that's exactly what we're trying to say there. Okay, and in the last sample interval, if you take a look at this, is initially what we got as the standard deviation of the estimator. We see a sigma. Because sample variance is consistent, it can replace that guy. That's no problem. Okay, that's all we mean. Now take a look at this. Okay, so here, what you see here, what we're trying to talk about here is that the moment at last sample size, if the estimator theta cap actually converges to true value of parameter theta, when I subtract theta from that divided by a standard deviation, it will approximately follow standard normal distribution. And why do I need standard normal distribution? Because I'll be able to make use of a z table. Does that make sense? Okay. Now, we actually have a theorem in statistics that provide a theoretical justification for that convergence that we call Slutsky theorem. Now, you know what Slutsky theorem is talking about. I told you something the other time that if I have a system is made up of components, right? If component, and every component has a true value. Now, if each component converges to their true value, then the whole system converges to the true value. An example, in the United States, you have like 50 states, right? Each state I want to believe before the start of a fiscal year, they actually have a target value in terms of what the economy should be. Now, if each state in a country achieve their aim, then the whole country has achieved their aim. That's what it means by Slutsky theorem. Okay, now take a look at this. Suppose that UN as a distribution function. Okay, if you take a look at this guy, initially this UN, okay, is not a standard normal. Initially, it's not. Okay, now it has a distribution function that converges, but it converges to a standard normal distribution at n tends to infinity, which means when sample size is what? Is large, the distribution function converges to standard normal distribution. And let me tell you this. If I want to prove that, if Wn converges in probability to 1, then, now take a look at this guy. What is happening here? Un has its own true value. Wn has its own true value. They are like components that have their true value. If they converge to their true value, the ratio will converge to the true value. The ratio here is, we're talking about ratio here. It could be subtraction. It could be multiplication. Do you understand what I mean? Now, if Wn converges to probability 1, then the distribution of this converges to a standard, normal function, okay? Because, Un divided by Wn converges to, in probability to 1. Now, if I really want to investigate, take a look at this. I'm going to say this, Un converges. When you see D, means convergence in distribution. When you see P, convergence in probability. Does that make sense? Convergence in distribution means the statistical architecture changes, the shape changes as what? As n tends to infinity. Now, if that happens, do you know what this guy, do you know the meaning of this guy? It means for every x in real number, for every x in real number, that's what this guy means. Okay, for every x in real number, if I now find, what do you think I want to find here? In statistics, give me 1 second. In statistics, when you see something like this, what does it mean? When you are looking at the probability of a random variable less or equal, that's a CDF. That's a cumulative distribution function. So if I, as initially, if I don't put a limit to n tends to infinity, it's not going to convert to standard normal. But it will convert to standard normal when I take the limit as n tends to infinity. What do you see? What you see here is the CDF of a standard normal distribution. Okay? That's a CDF of a standard normal distribution. That is what you see. Okay? So that's exactly what we mean here. Okay. Any question? Please, I ask question if you don't understand. Ask question. Do you know what I'm targeting for midterm 2 average? 99. Which is possible. Let's make it happen, okay? Let's make it happen. If you get stuck, I told you, reach out, okay? Now, let's come to example 9.4. Suppose that y1 up to yn is a random variable of sample size n from a distribution with expected value of y equal to mu, and the variance of y equal to sigma square, as you can see. Okay, you give it a sample variance to be equal to that. Show that the distribution function converges to standard normal function. Okay, we want to show that. Why did they give us this? They gave us that this is a sample variance, and what you see inside here is a sample standard deviation, and this guy is from this guy. Okay, let me tell you this. When components in a system are behaving good, then the entire system is behaving good. That's what I mean. Okay. Okay. Now I need you to take a look at this. We want to prove this. This is what we want to prove right now. We want to prove that this guy here, this guy here maybe this guy is UN. Okay. Maybe this guy is UN, a random variable. Okay. A random variable is a function of another random variable. There are 2 random variables in this picture, the mean and the sum and down. Okay, there are 2 of them. Okay, now we want to prove that as n tends to infinity, okay, we want to see whether that this guy converges to standard normal distribution. Now, if you want to do that, now convergence in distribution can be addressed by central limit theorem. Convergence of a statistic to a population parameter can be addressed by convergence in probability. Does that make sense? Now, and that is the reason here, because I want to talk about convergence in distribution, then I'm going to use the idea of a CLT. When I was talking about convergence in probability, I was using the idea of a large law of large number. Does that make sense? I was making use of law of large number. Okay. So please, I need you to see the difference between the two convergence. Okay. One in probability, one in distribution. The one in probability, I use law of large number. Okay. But the one in distribution, I'm actually going to use CLT, the central limit theorem. Okay. Now, I told you the other time, a UN equal to that guy, right? And by CLT, we want to tell the world UN converges to standard normal distribution. I told you from day one, central limit theorem facilitate normality. Normality facilitates standardization. That's what is happening here. Okay, just want to demonstrate. How are we going to demonstrate this? I need you to pay attention. It's very, very easy. I can assure you that. Okay, now I need you to pay attention to this guy now. Okay, let's say WN is XN divided by sigma. And we said something the other time. It will be to show that WN converges in probability to 1. How do we know W1 converges in? Oh my God, the WN is the ratio of sample standard deviation to population standard deviation. And of course, we proved the other time by law of large number. By law of large number, sample standard deviation can represent population standard deviation, then the ratio is going to be 1. Does that make sense? That is only going to happen when you are considering law of large number, and the law of large number is going to tell you probability convergence. Does that make sense? Any question about that? How WN converges to 1? Because WN is the ratio of a sample standard deviation to population standard deviation at a very large sample size. The sample standard deviation converges to population standard deviation. The ratio is actually going to be 1. Okay, and I just reminded you of this. Sample standard deviation converges to population standard deviation because sample variance converges to population variance. Okay? Because sample variance converges to population variance. Now, if G of S, and I want to move right now. If G of S equal to this, let's say for instance, the G of S is sigma square root of S divided by sigma. Okay. Now, do you know that if you take a look at this guy, if you want to look at the G of S squared, okay, the G of S squared, we're talking about function. The first one here is just a function of X. But this one is a function of sample variance. Function of sample variance. And right now, the square root of this guy is that guy, which is just going to be the ratio of sample standard deviation to population standard deviation. And we expect that ratio to be 1 when convergence in probability takes place. And what is convergence in probability that we always talk about? The convergence in probability is when a sample statistic or an estimator converges to the true value. And therefore, if that converges, the ratio of them will be 1. That's what we're saying. Okay, now that implies this guy now. Now, if that imply that guy now we now want to take a look at this. We want to work on this one. And don't forget that by central limit theorem or by law of large number, sigma is going to be replaced by Sn, right? Sigma is going to be replaced by Sn. Now, if you look at the way this guy is written, if you take a look at this guy, you just will write that guy as that guy mathematically. You've not altered anything. Now, when you have this guy now, okay, you're actually gonna see, you're gonna have opportunity to see that this guy here is UN divided by WN. Okay, so if you take a look at what you have there, and don't forget WN is more or less like 1. We said that WN converges to 1, 1. So WN, if this one converges to 1, then the whole thing is more or less like a I mean, it's like a UN. So that converges to that. That's what we mean. Now we're going to have a remarks. Okay. You know, the moment that happens, we can construct a confidence interval based on that. Because what are we constructing confidence interval on? Don't forget that's a WN, right? The WN, we can construct a confidence interval on on UN. We can construct a confidence interval on UN because UN has a standard normal distribution. Okay. And if you take a look at that, you know, I can say it lies between negative Z alpha over 2 and Z alpha over 2, which is equal to coefficient level. And of course, if I solve for mu, okay, if I solve for mu, I'm actually going to have this, which is the formula, which is a last sample confidence interval formula. Okay, I need to take a look at that. Now I want to go into example 9.4. Suppose y1 up to yn follow Bernoulli with parameter p. Of course, you know Bernoulli has a variance of p into 1 minus p. Okay, and of course the pn, I told you the other time, our sample proportion is different than sample mean. I told you the other time. Now we want to consider un again, except that the un that we are considering now, the focus is going to be on proportion. Okay, you know, p cap is the estimator. The p is a parameter. P into 1 minus p inside here is the variance. You know, don't forget, the variance of y is p into 1 minus p, right? Then you put a square root. You have this. Don't forget, I told you the other time. Okay, what you see there is the same thing as having you know, I got z equal p minus d, p cap divided by, what am I going to have here is p1 minus p divided by n. Okay, and if I have this guy now, if I want to rewrite this, I can actually do this square root of 1 minus p divided by square root of n. So this guy can be here, square root of n. Then I can write p cap minus p divided by square root of 1 minus p, which is what you're seeing right now. Can you see that? That's what you see right now. Now, the same thing that applies to confidence interval for mean also apply to confidence interval for proportion. We've done all this before. But we're just trying to tell you all these are possible because of the fact that the estimator has a tendency of converging. Okay? Okay. Now, can we use sample variance to estimate variance of y equal to p into 1 minus p? Please, I need you to pay attention here. Okay, I want to get it. I'm talking about a Bernoulli random variable. And I know the formula to be p into 1 minus p, but I may not know p. Okay, can we use a sample variance? And what is the sample variance? Of course, you know the sample variance is this, right? That is sample variance. Okay, now, and don't forget the other time, I show you how it can also become this. You saw a simplification I did the other time where sample variance can also be written in that form. Now, if it can be written in that form, if I want to figure out the variance of y, where y is the Bernoulli random variable, I need to ask myself, if y is a Bernoulli random variable, then y can take 0 or 1, right? it can take 0 and 1. And let me tell you this. If it can take 0 and 1, if y equal to 0 and 1, if I do y square, it's still going to be 0, 1. Is 0 square 0, 1 square 1. Because of that, what is going to happen? This is going to imply this. Y square equal to y. Does that make sense? Now, if y square equal to y, then please pay attention. Please pay attention. Now, take a look at this. Y bar will be P cap, and that will also going to be 1 over n summation y would be 1 over n summation y squared. They will all equal to y bar. They will all equal to P cap in Bernoulli distribution. And if that happen, you know what I'm going to do? Come in here now. I just want to plug in. Take a look at this. I want to plug in. That's what I'm doing here. What am I doing? Okay, I'm trying to say summation y, 1 over n summation y square is P cap. And since y bar equal to P cap, the square of y bar, that will be P cap square. Any question? I just plug that guy in here. Why? Why am I able to do that? If y is 0, 1, y square is also going to be 0, 1. So 1 over n summation y would be the same thing as 1 over n summation y squared. Can we see this? Is it also going to apply to y3? Y raised to the power 3? Yes. Because it's 0 times 0 times 0, 0. 1 times 1 times 1, 1. Does that make sense? Okay. Now, this is where we are now. What am I going to do here? Okay. I'm actually here now. I can factorize P cap out. That's common. That will lead to that. Any question? That was how we got that. Take a look at that. That was how we got that. Which means if I want to get my sample variance, I will just use that formula. But if you take a look at the top one, we don't know the true values of P. What are we going to end up using? We're going to use an estimator, an estimate that we got from the estimator. Does that make sense? That's what I mean. Okay. Now, if that can happen, if what we've done here, which means if the sample variance behaves well, okay, if I have another random variable that is a function of this, that guy will also behave well. Take a look at this. What do you see here? What is part of this? There are two well-known estimator in this formula: sample proportion and the sample variance. If the sample proportion can converge to P and the sample variance can converge to the population variance, the whole architecture will converge to standard normal distribution. And that was why I told you the other time, what if a system is going to be good if the component of a system are behaving well? Does that make sense? Okay, now if you do the same thing again, what do we want to do here? We want to plug in Sn. Where do we get the Sn? Let me go back. Where do you get the Sn? Oh, I've gotten, if this is Sn square equal to that, the Sn is going to be square root of the whole of that. Does that make sense? I needed to follow the way, see the way we're doing it now. So plugging that in, that was why you see here, you see the square root? You see the square root? Because we're focusing on Xn, which is the square root of that. Now look at where we are now. Now we are here now. All what we just need to do is to simplify. Okay. And we believe that this is going to converge in distribution to that. And if the convergence happen, then we'll be able to construct a confidence interval for that, which we always achieve using this. Okay. Now, in the next 5 minutes, I'm going to introduce you to another good property of an estimator, which we call sufficiency. And this estimator, oh my God, is I'm actually going to say is well ranked in properties of an estimator. Now we've done unbiasedness, we've done efficiency, we've done consistency. We want to go into sufficiency now. Okay, now I want to welcome you to sufficiency. But you know what? Because I'm still going to teach sufficiency in the next class, I'm just going to tell you the idea of sufficiency here. I want to use, I want to follow first, like, let me give you the application. I think what we're going to do next time, I'm going to walk you through mathematics of sufficiency, but let me first tell you the idea behind sufficiency, okay? What is behind the scene in sufficiency? And I want to use this in a criminal justice system, and I need you to listen. Now, look at what happened. It's a crime was committed in a particular area, okay, and police want to go into investigation. Are they going to interview everybody living in that area? Are they going to do that? No. They will only choose a sample, right? When they choose a sample and they tell the world we are done with our investigation, do you know what they mean? They mean the information they got from the sample is sufficient. There is no any other unselected individual in that population that has a greater information. That's what we call sufficiency. Does that make sense? That is exactly what we mean by sufficiency. We're trying to tell the world, oh, this statistic is sufficient. A statistic can be sufficient if it can give us what we need, what we want, about the values of the parameter, and there is no any other maybe person in the population that will give a better information. Does that make sense? That is what we mean by sufficiency. Now, if you understand what that means, and I'm going to take it to mathematics. Don't go into mathematics without understanding the intention, without understanding what is behind the scene. Mathematics is not going to make sense if you don't know what is behind the scene. Like what I'm going to be telling you now is going to make sense to you because you know what sufficiency actually means in the actual sense. Now, let's say for instance we want to consider sufficient statistic now. What make a statistic to be sufficient? I have a statistic. I have an estimator. How am I so sure this estimator will give me what I want? And there is no any other unselected sample that will give me better information. Then this is how to tell. If I consider outcome from n trials of binomial experiment, look at that. N trial, which means I'm not going to ask, it's not going to be everybody in the population that I'm going to interview. Where SI equal to 1 or 0. Oh, look at that. When police go to the crime scene, when they take a sample, they're going to ask from this guy, okay, are you the one? What do you expect? So he's going to say yes or no. That is what make it binomial. And we're going to do 1, 0. 1 will be I trial is a success. Do you know what's going to be a success to the police? They were able to get the guy. And it's going to be failure if that guy is not the one. Does that make sense? Okay. Now, if P is the probability of success, whether failure or success, there's always going to be probability associated with them. When somebody fail, there's a probability of failure. When somebody pass, there's a probability. So now we're going to say, X here is actually a categorical. We label that 1 and 0. 1 for the event of success, 0 effect of failure. We're going to say, okay, let P represent the probability of success. And let 1 minus P or Q represent the probability of failure. Does that make sense? Okay, now if that really makes sense, do you know what I want to find? Take a look at this. Oh my God. Police really want to figure out the numbers of criminals that commit the offense because the offense may not be committed by just one at times. Does that make sense? Which is going to be why you go to sub. Oh my God, my time is up. My time is up. I'm going to continue from here on Wednesday, but you already know what is behind the scene. Any question? Any question? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.